So I am professor at Centrale Supelec and researcher at LBZ, like Marco, who presented earlier. And I will present some a work that is an aggregation of some paper results, all about the Aloha-like schemes in the uplink. So just to recall the scenario that you now I have to confirm. So this is the same scenario that you have seen before. So we are in some plant or in some industrial site, and we have a set of devices that may be machines or robots or vehicles that want to convey some packets to a fixed network to a central controller. So this talk will be about the radio interface only. We do not consider anything, any delay on the fixed backhaul or network that is there. And the objective is simple. It is so each of the devices will generate sporadically some packets, and the objective is that the proportion of packets that are received at the base station within a delay budget, for example, one millisecond, is larger than a target. So typically, we have seen this in these two days. The probability, the loss probability, should be less than 10 minus 5. So I will begin by introducing the classical resource allocation in the uplink. So here you are in the uplink. We are using contention-based as in classical Aloha, and then I will explore the impact of knowing what happened. So blind and farsighted, it is with respect to if we have received a feedback from the network that says that the packet has been decoded or not. So I will explain this in the slides. But so how the standards in 5G has how the 5G standard has defined schemes to ensure the 10 minus second packet loss. So to be clear, it is not a packet loss here. It is the definition that the packet is in outage. So the packet may be not lost, but it may arrive after the 1 millisecond target. So what has been done in the standard that the so-called semi-persistent scheduling has been defined. So if you have a set of user equipments, it's they wanted in the standard to copy the IEEE TSN. So they said we have the time and frequency resources, and then in each frame we will reserve a quantity of resources for each of the devices, so that if this device has a packet to send, he will know exactly where to send. So in the standard, it's OMA. There is no NOMA, and it has been defined for deterministic traffic, saying that in each cycle, each user will generate exactly one packet. So if we reserve resources for each of them, we don't have a loss and we don't have any delay. So this may work for a small number of users, and this also may work when the traffic is periodic, meaning that each user has exactly one packet per cycle. So for example, if you have 6 users and the deterministic traffic with this example of moderation and encoding, and you need an amount of spectrum equal to 1.4 megahertz. If now we have 60 users, and each of them will generate a packet at probability 0.1, you will need 14.4 megahertz. So you all see that this semi-persistent scheduling is not scalable. That's why even in the standard, people are now talking about contention-based access for the uplink. So I recall that the scenario we have a very large number of users that generate sporadic traffic, and we don't reserve any resources for each user, but we have a pool, and we apply Aloha-like scheme. So in this example here, we have a set of users. When a user generates a packet, he will choose at random one of the slots in time and frequency, and he will send this packet. The obvious thing is that the reliability cannot be achieved. So Paul asked me if it's really possible. It's not possible to achieve it with Aloha. So it is very easy to show it, and that so the loss, if the probability of generating a packet during a slot is equal to Q, and you have K resources, the equation of loss is this one. If you have n users, and then if you plot the required number of resources K in the spectral dimension function of the number of users, we can see that. So the red curve here is the deterministic allocation. So you allocate one slot per user. So it's with a slope of 1. But so if we need a loss that is equal to 0.1, Aloha is good. If we need a target loss of 10 minus 3, Aloha is not good at all. So after this introduction, so what we are doing in this paper is that we make use of a scheme that is similar to the p-persistence Aloha. So instead of sending each packet once, you send the packet several times within the delay budget, and then our objective is to ensure that the number of resources are sufficient for obtaining the target outage of 10 minus 5. So now let's see what happens when we take a look to the standards of 5G. So in 5G, we have the possibility of receiving a feedback. So there are many different frame types in 5G. So here I give an example of the time division duplex. So for example, here we have different types of frames. We are in the uplink, so we can see that in some types of frames, we have an opportunity of sending a packet only in one slot in a frame. So here you can see that even if you receive a feedback on one of the downlink, so here you send your packet on the uplink slots, and then you might receive a feedback on one of the downlink slots. But then when your turn comes again on the uplink slot, the delay budget expired. So in this case, you do not have any feedback from the network. In different cases, you might have some time here. For example, here, if you send your packet in this position, you receive a feedback on this position, and then you can send the packet again. So you can see that depending on the configuration of 5G, sometimes you might receive some feedback, and sometimes you cannot receive a feedback. So for example, if you have this DDDU frame, meaning that you have a slot for downlink, a slot for downlink, a slot for downlink, and a slot for uplink. You can, and if you have 1 millisecond delay target, you cannot have any feedback from the network, and you cannot replicate the packet in time. So your only option is to replicate in spectrum, send multiple replicas in spectrum. If, for example, you have this UUUD uplink downlink, you can replicate your packet in time. You can send in different slots different replicas of the packet, but you won't receive any feedback from the network. So this is what I call blind repetition in time. And if you take, for example, the FDD frame, so you have separate sources in downlink and in uplink. You will send your packet at some time. In downlink, you will receive a feedback after some slots, because the base station has to decode the packet and send the feedback. So you might receive a feedback in some time, and when you receive the feedback, you stop sending the packet. So that's what I call delayed feedback. And in this case, you are not blind, but you see only the result of an action that you have taken in some time in the past. This means that even if a packet is decoded, you may continue sending a replica until you receive the ACK. So I will start by the schemes, by the configurations where you are completely blind, and see what is the optimal transmission policy if you want to reach the target outage. So the hypothesis is that I have these slots where I can send replicas of the packet, and I will not receive any feedback about it. And I adopt the P persistent Aloha. So at which, so when the packet is generated for the first time, we send the packet, and then in the subsequent slots, we send a replica of the packet with a probability P, and P is less than 1. So here we have an example. I will not detail things, but we can see that this might be good, because the probability of decoding will increase. So the hypothesis here is that I do not combine packets. So if a packet is in collision, it is completely lost. So we can introduce into the models the case where we can do chase combining, for example. But in this work, I didn't do it. So here we have the first result that it's based on a simple computation of the probability of loss. So the probability of loss here is the product of two factors. So the first factor here indicates that. The first factor indicates that the first transmission of the packet is lost, and it's lost if it is in collision with one of the other users. And the second factor says that each one of the subsequent d-1 replicas of the packets is lost. So we can see that this probability of loss depends on the probability Q of having a packet generated in one slot. We suppose that the traffic is homogeneous, so all users have the same probability Q. And then also we suppose that all users follow the same policy P. So if I send a replica with probability P, the other devices also send a replica with probability P. So it's like if we have a centralized controller that decides that P and broadcasts the value of P to and everyone applies it. We have also shown that this can be modeled as a game that will converge to this value of P. And also we have a strong hypothesis here that say that traffic is cyclic. So the activity probability is small. So when you generate a packet, you have a delay budget of D, but you will not generate another packet within this delay budget. So you in each cycle D, you have only at most one packet. So this equation here is easy to implement, but we also can find an easier upper bound that can be optimized analytically. So we have shown that an upper bound of the value of loss that we have obtained before is this one, and then this is unimodal, and it has a unique value of P that minimizes the loss, and it is obtained by this equation. So if the number of users is larger than a threshold, this is the value of the probability P with which we have to transmit. And otherwise, if we have a low number of users, we transmit with probability of 1. So this loss starts decreasing and then achieves a minimum and then increases. So what is the mean of what we see here? That for some value of the number of devices you have probability of 1. This means that for a low load, for example, if the number of users is small, perhaps it's better to send more than one replica in each slot. So P persistent Aloha sends at most one replica in each slot. So why not exploring a different scheme that instead of sending P between 0 and 1, we send multiple number of packets in each slot. So the example here is that with P equal to 2, we send each packet twice in each of the slots within the derive budget. And we seek to find what is the probability of loss when we have P larger than 1 and to optimize it. So I will not enter into the details of the computation, but we have used some simple combinatorial techniques to find the probability of loss in this case. So this case is the one where you have more than one replica of each packet sent in each slot, and this is repeated times. And then what we observe here is that, so if we make if we plot the probability of loss, so if we plot the probability of loss here, function of the policy P, so here it is a scale, a logarithmic scale, because I wanted to show P between 0 and 1. So this is P persistent Aloha. The blue curves are P persistent Aloha, and the red curve is the case where P is larger than 1. It is integer larger than 1. We can see that if P is equal to 1, both schemes give the same thing, because this is exactly the same scheme. And then depending on and then depending on the value of traffic, we can see that the optimal value of the policy P can be lower than 1. So if, for example, for this curve, we have a very large number of users. So for a very large number of users, it's the optimal policy is to send less than one packet per slot. And for a small number of users, the optimal policy is to send more than one packet per slot. But you can see that to achieve 10 minus 4 or 10 minus 5, it's always be larger than 1. So if you want to achieve the analysis targets in the contention-based schemes, you have to consider only very low traffic, very low number of n, and also to consider to send more than once the packet in each time. So here it's only an illustration that says, so we have two curves. The blue one is the optimal policy in the P persistent Aloha, and the red one is the optimal policy when P can have values larger than 1. And we can see that it is better for small n, for a small number of devices. It's better to send more than once the packet in each slot. And for large number of n, it is better to use the P persistent Aloha. So now I will move to the case where the network will send a feedback within the delay budget, and then you can react and readjust your policy. So the example that I have shown before is that you send your packet, multiple times, and then in some of the times the packet is received without collision, so it is decoded, but the base station does not yet send you the ACK. So you in the next slot you resend the packet because you don't know if the packet has been decoded. When you receive the ACK, you stop sending. This means that the load here is lower than the load when you are blind. And to illustrate this, we can plot the activity of users. So the activity of users is the average number of packets that are sent per slot. We can see that if you are blind, so the value of Q is constant, but when you send the packet multiple times, this means that each packet is sent multiple times, so the activity increases. So if you are blind, the activity is high, is constant, and if you receive some X, the activity may be low when the number of users is low, and it becomes very high when the number of users is high. So we have started by modeling the Oracle case. So in this case, it is not possible in practice, but we suppose that when you send a packet, you know instantly if the packet has been decoded or not, and you stop sending. So in this case, we have also obtained the value of the loss as a product of two expressions. The first expression is the probability of loss of the first packet, and the second expression is the probability of loss of the replicas that are sent afterwards. And this depends on a function that is called here beta p. So L1 and L2 are the probabilities of loss, but beta p is the probability of having a collision with one of the other users. So I have said that all users will apply the same policy P. So if you are sending with probability P, other users are also sending with the probability P. And then if other users have already received an ACK, they will send the packet with a lower probability. So we see that there is a fixed point. So the probability of loss depends on a function that is beta of P, and beta of P depends on the probability of loss, L1 and L2. So L1, L2 depends on P, on beta, and beta depends on L1, L2. So we can solve a fixed point, and the role of the fixed point is to know for each value of P, what is the average number of times each packet is sent before it is stopped because it has been decoded. So we can also see this as a game, and the result of the game will give you will give you the optimal policy P. So we can show that as it is expressed as a fixed point, it's like a mean-filled game, and then the result of the fixed point will give you the equilibrium of this game. So, and then I said that the previous slide was when you have an oracle that tells you immediately that your packet has been decoded. When you have the ACK received after some delay, you are no more an oracle, but you receive information about a delayed action. So we have proven that the packet loss in this case can be derived function of the packet loss in the completely blind case, but by decreasing the activity factor. So the activity factor of the different users will depend on the success rate of the protocol. So if the success rate is higher, the users will send less packets per slot. So we again have here a fixed point that you have to solve to obtain the loss. So here I give you some hints about how we obtain the activity factor of users, but the takeaway is that we can consider the loss for a completely blind system, and then take into account that when you are not blind, you receive a feedback from the network, so your activity is lower. So you modify the value of Q, and instead of putting Q in the equations, you put Q bar, which is the new activity factor. So here we have the case. I compare in this figure the case of the in both cases we have a delayed feedback. So we have a device, a transmitter that is far sighted. The first case in that is the P persistent Aloha, and the second case is when you send multiple packets per slot. And we see as before that the P persistent Aloha is better when the number of devices is high, but you cannot achieve any good performance with it because the loss remains high. And then sending multiple replicas per slot is better in the low traffic regime. So I hereby reach the conclusion, but it will not be a classical conclusion, because our objective was to see what is the optimal policy in different scenarios of 5G. So we have derived different formulas for the loss rate, supposing that you receive a feedback or you do not receive a feedback. So what I put here is that I have taken 6 configurations of the standard of 5G. So the different configurations have different value of the subcarrier spacing. So it's 15 kilohertz or 30 kilohertz. And then you have different number of symbols per slot. So we have the scheduling on the basis of mini slots for URLC. So in each of these configurations, the size of the slot is different. And then in some of them you use FDD, in some of them you use TDD. And then based on this configuration, I have computed the capacity. So how many packets I can put per slot. And I have also received, if I can receive a feedback and within the delay budget or not. And the objective, so in each case, if you can receive a feedback, you apply the policies derived in the far sighted regime. And if you are blind, if you don't receive any feedback, you apply the policies that we have derived for the blind. And then configurations 1 and 2 can be compared between them, because we have 10 megahertz for downlink. Configuration 3 and 4 are FDD, so it is 10 megahertz divided between downlink and uplink. And then we have compared the different the packet loss function of the number of users for these 6 different configurations, and we can see which kind of configuration is better if we want to use RLC. 5 minutes or okay. So a few slides about the perspectives. So what we have did in this work, it was in the uplink. So we have contention-based. And the meaning of we started by looking at contention-based because it's difficult to solve. And people say that in the downlink, if you have grant-based scheduling, things are easier. But we have also explored what happens in the grant-based scheduling. So in this case, you have a queue at the base station. So you are in the downlink, you have a queue, you have packets that arrive. So arrivals are typically not Boston. And then the service is in discrete time because the time is in slots. So this is a discrete time queue, and the arrivals are not Boston, and the service is not exponential because usually you serve one packet or per slot. And we have shown in Compare that we cannot neglect the queuing delay. It's better than in the uplink, but the queuing delay might be important. So if the objective is to ensure that the probability of delay does not exceed a threshold, so we have different approaches. We modeled the system as a discrete time queue, and we can approximate also it by a continuous time queue. For example, in this particular case where you have one resource per packet per slot, you can approximate this by an MDC queue, and you can obtain the distribution of the delay and find the value of C, the number of servers to have a delay of 1 millisecond in 99.99% of cases. A second approach also is to use large deviation bounds and to say that you have accumulated traffic here, and you use the large deviation bounds to see what is the optimal number of resources that you have to put. Or perhaps we can use also stochastic network calculus. We have seen from the presentation of this morning that this might be very interesting to apply in this case. So this is what we have done from this perspective of performance. But the question here is we have solved a problem, but is this the real problem to solve? So in the standard, they say 99% of packets have to be received within one millisecond, but is it really a good constraint in real networks? So we have taken an example. So we have simulated a platoon of vehicles on a highway, and then you have communications between the vehicles. So the first vehicle sends packets to everyone to say that there is a problem behind of it, and we would like to see what is the impact of losses. So if this packet is lost, is it really bad? The objective is to minimize the distance between the different cars. So we have simulated the platoon, and we have also implemented the controller. So when some user receives a packet, he will adjust the acceleration to avoid collision with the others. So each of the vehicles receives information from the head and adjusts independently his acceleration on this. And we can see that for a packet error rate that is between 0 and 10%, we can reach very good performance. So 0.4 meters between cars in the platoon. So you cannot physically go down this. This means that the loss of packets is not very important in this kind of system. So what to do? So this is a link to the presentation of Marius before. Instead of having this generic target of having 10 minus 5 outage, why not using this goal-oriented communication framework? So what is done is that you optimize the network and the application in the same time. So here we have an example where in the platoon, depending on the measurement of the quality of the links, the controller will try to have cars to increase the distance between cars to avoid collision. So you optimize in the same time the quality of the network and the application itself. So I am done. Thanks to my co-authors from Orange, Télécom-Paris, and Centrale Supelec. And here are some of the papers that contain the results of this talk. So we have the first set is on the contention-based. The second one is on the large deviation bounds, and the last one on the goal-oriented communications.